US Physics Olympiad, year 2022, USAPHO, final round. This examination had two parts. Part A had 3 problems for 90 minutes, and Part B also had 3 problems for 90 minutes. Problem A1. Moment of clarity. Hold your pencil horizontally by its tip. To keep it still, you will have to exert a combination of forces on its bottom and top. These forces can be viewed as a superposition of a net upward force and a pair of opposite forces. The former ensures the force on the pencil and balanced, while the latter provides a torque called the bending moment, which ensures the torques on the pencil are balanced. Since the bending moment arises from a pair of opposite forces, it doesn't depend on the choice of origin. Question A. Consider a rod of length L and mass per length lambda. What is the bending moment you must exert to hold the rod horizontally at its end? Just as each piece of string exerts a tension on the neighboring pieces in equilibrium, each piece of solid rod also exerts a bending moment on its neighbors. For these rods under heavy loads, this bending moment can be the limiting factor that causes them to break. Suppose a rod is supported at both ends, so that it forms a bridge as shown at left above. Assume the supports are simple, so that they only provide an upward force and no bending moment. In equilibrium, a bending moment will appear throughout the rod. The magnitude of the maximum bending moment the rod can exert at any point without breaking is m0, and the length of the rod is L. The bridge is loaded uniformly, with a mass per length of lambda, including its own mass. Question B. Now suppose that one support remains at the left end, while the other is a distance d greater than L/2, away from the left end, as shown at right above. In static equilibrium, find the bending moment m as a function of m0 at distance x0 less than d from the left end. Question D. Find the value of d that maximizes the load lambda that the bridge can take before collapsing. Solution for problem A1. Solution for question A. Consider a rod of length L and mass per length lambda. What is the bending moment you must exert to hold the rod horizontally at its end? Solution. Balance torques about the end of the rod. The weight is lambda GL applied uniformly along the rod, so the torque due to gravity is lambda GL square over 2. This can only be balanced by the bending moment, so it is lambda GL square over 2, and this is the solution for question A. Solution for question B. Find the maximum possible value of lambda before the bridge collapses. So before that, just read these conditions. Solution. Let's take a look for this picture. If we take origin as a left end, so it means that x equals 0 here. On right end we have coordinate is x equal L. Let's take point on distance x from 0. Around this point we have to calculate all forces and angular momentums from external forces. There are two external forces. One is force from this left support, which is equal to lambda GL over 2, and it's going upward. And also we have weight, which is lambda GX. These two forces created two torques. One torque is lambda GLX over 2. This is clockwise. And the other torque is negative lambda GX square over 2. And negative because it's counterclockwise. So together they will give us total torque from external forces, which is this expression. And these two torques from external forces, they must be compensated by internal bending moment. So it means that this bending moment must be opposite to this one, which is this expression. Finally, we need to find what is the maximum for this function in absolute value. That will be for x0 equal L over 2. So finally, m0 equal lambda GL square over 8. And lambda will be 8m0 over GL square. I can notice that same result we will get if we take in account all forces and torques from right side to point X. And this is obvious because the bending moment from left must be equalized in the same point by bending moment to the right. So this was a solution for question B. Question C. Now suppose that one support remains at the left end while the other is a distance d greater than L over 2 away from the left end, as shown at right above. In static equilibrium, find the bending moment m as a function of x0 at a distance x0 less than d from the left end. Solution. Here, for static equilibrium, we need to equalize total force and total torques to 0. So, total force from right and left supports equal to lambda GL. Now, let's count what is the torque around any point. Let's take left support as the origin. We have torque from the right support equal Fr multiplied by d. And that's equal to weight torque from left part to torque from all weight, which is lambda GL square over 2. From here we can find that Fr equal this expression and Fl equal this expression. Now let's count what is total external torque to the left from the point x0. That will be torque from left support, which is Fl x0, because it's a clockwise. We need to subtract counterclockwise torque from weight, which is lambda g x0 square over 2. And our bending moment must be opposite to this one, which is this expression. That was solution for question C. We just need to emphasize that d must be more than L over 2, because if it's less, in that case we have to put negative force on the left side or just push it down, which is not question of this problem. That was solution for question C. Solution for question D. Find the value of d that maximizes the load lambda that the bridge can take before collapsing. Solution for this question. If the bridge doesn't collapse, then the magnitude of the bending moment must be less than m0 everywhere throughout the rod. Consider how the bending moment varies as one moves from the left end of the rod to the right. It begins at 0 when x equals 0, in the expression which we got in question C. Then reaches a positive maximum somewhere between the two supports when first derivative from this function equals 0. This occurs when x equals L minus L square over 2d, at which point there is a bending moment of m1 equal this expression. As a check, we recover the answer to part B when d equal L, and this is correct. Continuing rightward, the bending moment decreases, passes through 0 at some point x less than d, and then becomes negative. This change in sign is necessary to support the part of the rod hanging to the right of the right support. At point x equal d, the bending moment does not change discontinuously, because the supports provide no bending moment. It then smoothly returns to 0 as x approaches L. Therefore, the most negative value of the bending moment occurs when x equals d, giving the bending moment of magnitude m2 equal this expression. As another check, this matches the answer to part A for a rod of length L minus d, which is correct. As we move the right support closer to the center, the middle of the bridge becomes more stable, since m1 decreases. At the same time, m2 increases, because more of the bridge is hanging off the edge of the right support. The bridge will not collapse as long as both of these quantities, m1 and m2, are less than m0. Thus, when the right support is placed most efficiently, both of them will become equal to m0 just before the bridge collapses, which means we should have at some point m1 equal m2. Equating them yields which gives the answer. This equation gives us solution for point D, which is d equal L over square root from 2. That was solution for question D, and here we finished discussion for problem A1. US Physics Olympiad, year 2022, USAPHO. Final round. Problem A2. A droplet of liquid metal has a constant mass density and constant surface tension sigma, which causes it to form into a sphere of radius r. Throughout this problem you may neglect gravity. A thin wire is inserted into the droplet and connected to an electric current source which slowly charges the droplet. There is a critical value of the charge Q0 that causes the droplet to split in half. Each half takes half the total charge Q0 over 2 and half the mass of the original droplet. The eject half is repelled far away from the other half, which remains in contact with the wire. Question A. For simplicity, assume the droplet splits as soon as the final state, after the droplet has split in half and the two halves are well separated, has a lower total energy than that of the initial single droplet. What is the value of Q0? Give your answer in terms of a dimensionless constant A multiplied by a product of powers of sigma r and the vacuum permittivity epsilon 0, and give the numeric value of A to three significant figures. Question B. As more charge is added to the droplet by the current source, it continues to split in half repeatedly. What is the charge Qn of the nth ejected droplet. Give your answer in terms of Q0. Question C. In the limit where all of the initial mass of the droplet has been ejected, what is the total work done by current source? Give your answer in terms of a dimensionless constant B multiplied by a product of powers of sigma, r, and epsilon 0, and give the numeric value of B to 3 significant figures. Solution for question A. For simplicity, assume the droplet splits as soon as the final state, after the droplet has split in half and the two halves are well separated, has a lower total energy than that of the initial single droplet. What is the value for Q0? Give your answer in terms of any dimensionless constant A multiplied by a product of powers of sigma, r, and the vacuum permittivity epsilon 0, and give the numeric value of A to 3 significant figures. Solution. From dimensional analysis we can find that Q equal to constant A multiplied by square root from epsilon 0 sigma r cube. To find the value of A, note that a droplet of radius r has a surface energy 4 pi r square sigma, and an electrostatic energy is Q0 square over 2c, where c is 4 pi epsilon 0 r, is the capacitance of a conducting sphere relative to infinity. Thus, total energy of the drop is this one, the sum of these two energies. When the droplet splits, the new halves both have charge Q0 over 2 and the radius r over 2 power 1/3, since the total volume stays the same. The total energy of each of the halves is thus this one. Setting E equal to E1 and solving for Q0, this equation, we will have this equality, which can give us a solution for Q0, which we got from dimensional analysis, and constant A equal this expression, which is approximately 14.9. This model is of instability of a charged liquid drop is not exactly accurate, and was chosen to keep the problem simple. In reality, it isn't enough for the final state to have lower energy. The repulsive electrostatic force needs to exceed the surface tension force, or else the bubble can't get to this state of lower energy. So in this case we can give you more accurate solution. We already counted that total energy is this expression, which consists of surface tension energy and electrostatic energy. First one creates inward force and the second one outward force. So when we add an additional Q0, we can increase force from electrostatic, which can reveal the surface tension force. To find what is point of instability, we can just take this energy and take first derivative by r from this energy and equalize it to 0. That will give us equation this one, and from here we can find that Q0 equal 8 pi square root from epsilon 0 sigma r cube, and the constant A equal 8 pi, which is approximately twice greater than in previous solution. Another way to solve this problem is not energy but force approach. We know that the electrostatic field just near the surface of this droplet from outside equal Q0 over 4 pi epsilon 0 r square. This field created by small area delta S and the rest of this droplet surface. We know that electrostatic field due to Gauss law, the difference between electrostatic fields from both sides equals exactly to this expression. So it means that because inside of this droplet we have electrostatic field is 0, so it means that total electrostatic field from rest of this droplet equal to half of this expression. And now we can count what is force delta F1 acting on a small charge delta Q on small plate area delta S. That will be this expression. And now to find what is pressure created by this electrostatic field, we can just divide this force by delta S, which will give us pressure P1 equal Q0 square over 32 pi square R power 4. And this pressure pointing outside. Now let's count what is the pressure due to surface tension, which is pointing inside of this droplet. We know that total force acting on a line of length L equal L multiplied by sigma, coefficient of surface tension. And if we take a small circle radius small r on this droplet, we can count what is the force acting on this surface inward, because for small radius r of this surface it takes volume angle which has regular angle 2 delta alpha, and the total force equal circumference of this area, which is 2 pi r multiplied by sigma, and we have to multiply it by sine delta alpha, which for small delta alpha just equal delta alpha. And now to find what is the inward pressure, we need to divide it by pi r square. That will give us 2 sigma delta alpha over r. But taking in account that small r equal radius of droplet r multiplied by delta alpha, finally we will get P2, pressure from surface tension, equal 2 sigma over r. Now we have to equalize these two pressures to find the critical Q0, after increasing which we will get electrostatic pressure will prevail surface tension pressure. Equalizing these two expressions, we will get same answer as for energy approach. So Q0 again equal 8 pi multiplied by square root from epsilon 0 sigma r cube, which is correct answer. Now we presented all three approaches for this question. Solution for question B. As more charge is added to the droplet by the current source, it continues to split in half repeatedly. What is the charge Qn on the nth injected droplet? Give your answer in terms of Q0. Solution. Consider the situation just before the number n split. At this point, the initial droplet has split in half n minus 1 times, so it has a volume that is 2 power n minus 1 times smaller than the original volume, and thus the radius is r divided by 2 power n minus 1 divided by 3. By part A, the charge required to split this drop is Qn equal Q0 over 2 power n minus 1 over 2. Once the split happens, the number n injected droplet takes half of this charge. So Qn equal Q0 over 2 power n plus 1 over 2. Also note that the radius of this droplet is r over 2 power n over 3. So that was solution for question B. Solution for question C. In the limit where all of the initial mass of the droplet has been ejected, what is the total work done by the current source? give you answer in terms of a dimensionless constant b multiplied by a product of powers of sigma r and epsilon 0, and give the numeric value of b to 3 significant figures. Solution for question C. By dimensional analysis, the total work W done by the voltage source must be B multiplied by sigma R square. The work W is equal to the difference between the energy EF of the final state, where there are many small droplets that have been dispersed too far away, and the energy EI equal 4 pi sigma r square of the initial uncharged droplet due to surface tension. The final energy includes the surface tension and the electrostatic energy of all the small droplets which have a radius Rn and the charge Qn found in the previous problem. This means that the final energy is this one. Using results from part B, we can rewrite this sum as, putting all numbers from part B, we will get this total final energy, and to find what is work, we need to subtract from this initial energy 4 pi sigma r square. And finally coefficient B will be this one, which depends from constant A 14.9, which was given in the first approximation, or 8 pi, which was counted in more precise estimation. So that was solution for question C. Now let's do more correct way to solve this problem. The suggested before was that we have to count what is potential energy for drops which were far away, but in that case we didn't count what was the kinetic energy which was produced during electrostatic interaction between droplets. We could suggest that one remaining droplet is not moving. In that case, all kinetic energy was received by moving away droplets. So in that case we don't need to count what is the initial potential energy of initial not charged droplet. It was 4 pi r square sigma, because we just need to count remaining energies for droplet. Let's do this. First, droplet was charged from 0 to charge Q0, so that was initially given energy. And after that we can just count what is the energy difference between start to divide droplet and the energy of remaining droplet. Let's do this. So energy of the initial droplet just before division was 4 pi sigma r square plus Q0 square over 8 pi epsilon 0 r, where Q0 was A multiplied by square root from sigma epsilon 0 r cube. Now after division, the left droplet was with the energy E1, where we use a new radius R1 and new charge Q1. New radius was R over 2 power 1/3, and Q1 was Q0 over 2, and E1 in that case was this one. Now we can count what is the energy difference between initial energy E and the remaining energy E1. This is what we really need. And now let's do recursion. We have delta En equal this expression, and finally we just need to summarize all this delta E by N. That will be all this sum. And we see that this all going to sum of geometric progressions, which finally give us this result. Now we need to add initial energy given to initial droplet. So that was q0 square over 8 pi epsilon 0 r. When we add them and also refresh that q0 was this expression a multiplied by square root from sigma epsilon 0 r cube, and also we counted that a was 8 pi. And the last step, we have to subtract initial surface tension energy 4 pi sigma r square. In that case, total energy which was receiving from current source was this one, and the coefficient beta was 4 pi multiplied by 2 power 8 over 3 plus 2 power 2 over 3 minus 2. That was correct solution for question C. US Physics Olympiad year 2022 USAPHO final round. Problem A3. Rainbow road. In geometric optics, a caustic is a bright curve of light that appears when many oncoming light rays are focused in the same outgoing direction. The most famous example of the caustic is a rainbow, which occurs when light interacts with the spherical water droplets. Consider a spherical liquid droplet of radius r with the index of refraction 1 less than n less than 2, suspended in air with index of refraction n equal 1. Question A. Consider a light ray that enters the droplet with the impact parameter b, reflects one of the inside surface of the droplet, then exits, as shown at the left below. Give your answer in terms of the dimensionless impact parameter x equal b over r. Hint: the four marked angles are congruent. First, find the angle by which the light ray is deflected at the first refraction. Second, find the angle by which the light ray is deflected at the reflection. Third, find the angle by which the light ray is deflected at the second refraction. The sum of these three quantities is the net deflection angle phi as a function of x. The light can also reflecticide more than once or never either at all, but for simplicity we will ignore these other paths. Question B. Next, we consider when caustics form in general. Suppose the droplet is uniformly illuminated by parallel light rays of intensity I0 and sits at the center of a spherical screen of radius big R much greater than small r, as shown on the right above. Consider the light that enters near dimensionless impact parameter x0 and exits near angle phi0 equal phi from x0. First, what is the power incident on the droplet of x0 less or equal x less or equal x0 plus dx? Second, what is the area on the screen illuminated by the outgoing rays at phi0 less or equal phi less or equal phi0 plus df? Third, a caustic occurs when the intensity of light on the screen diverges. Assume that phi0 not equal 0 and phi0 not equal pi. Under what conditions does the light incident at x0 lead to a caustic at phi0? Express your answer as a condition on the function t from x. Question C. Find the angle phi0 of the rainbow in terms of n. Hint: the derivative of arcsine is 1 over square root from 1 minus x squared. Question D. For water, the index of refraction of red light is 1.331 and the index of refraction of blue light is 1.340. Find the angular width of the rainbow on the screen and give your answer in degrees. Question E. A glory is an optical phenomenon which involves light scattered directly backward at phi equal pi, leading to an apparent halo around the shadow of an observer's head. For what value of n is there caustic at phi equal pi? Can glories from water droplets be explained in terms of caustics? Solution for question A. Consider a light ray that enters the droplet with the impact parameter b, reflects once of the inside surface of the droplet, then exits as shown in the picture. Give your answers in terms of the dimensionless impact parameter x equal b over r. Hint: the four marked angles are congruent. First, find the angle by which the light ray is deflected at the first reflection. Solution. The angle the incoming light ray makes to the normal of the droplet is θ1 equal arcsine x. By Snell's law, the angle to the normal inside the droplet is θ2 equal arcsine x over n. The first refraction causes a deflection of θ1 minus θ2 clockwise. So that was the answer for question I. Second, find the angle by which the light ray is deflected at the reflection. Solution. The reflection keeps the angle to the normal the same and causes a deflection of 2 pi minus 2 θ2. This was the answer for the question II. Third, find the angle by which the light ray is deflected at the second refraction. Solution. At this point the angle to the normal is still θ2 and by Snell's law it reverts to θ1 outside the droplet. This causes a deflection of θ1 minus θ2 with the same sign clockwise as in part I. Thus we conclude the total deflection angle as a function of x, phi x equal 2 pi minus 4 θ2 plus 2 θ1, or this expression 2 pi minus 4 arcsine x over n plus 2 arcsine x. That was solution for question A. Solution for question B. Next, we consider when caustics form in general. Suppose the droplet is uniformly illuminated by parallel light rays of intensity I0 and sits at the center of a spherical screen of radius big R much greater than small r, as shown at the picture. Consider the light that enters near dimensionless impact parameter x0 and exits near angle phi0 equal phi from x0. First, what is the power incident on the droplet at x0 equal or less x and the x equal or less x0 plus dx? Solution. The region with the impact parameters in this region is a thin annulus with the radius rx0 and the cross-sectional width r dx. Then the area of this annulus is this one, 2πr square x0 dx, and the power is I0 ds, or 2π I0r square x0 dx. That was solution for the first one. Second, what is the area on the screen illuminated by the outgoing rays at phi0 equal or less phi and phi equal or less phi0 plus d phi? Solution. By similar reasoning to the previous part, we have radius of illuminated area on the screen is big R sine phi0, and the cross-sectional width is R delta phi. So the total area will be 2π big R square sine phi0 d phi. That was a solution for second. Third, a caustic occurs when the intensity of light on the screen diverges. Assume that phi0 not equal 0 and not equal pi. Under what conditions does light incident at x0 lead to caustic at phi0? Express your answer as a condition on the function phi from x. Solution. By dividing our two answers, first one by second one, we will find intensity on the screen is delta P over delta A, which is I0 small r square by big R square multiplied by x0 over df over dx multiplied by sine phi0. This diverges when the denominator becomes 0, which in this case only occurs when first derivative of phi by x in point x0 equals 0. That is, caustic will occur at this condition. Intuitively, this condition means that a broad range of incoming light rays and up focused on a narrow curve on the screen. So this is the condition for caustic, and this was the answer for the third one. Solution for question C. Find the angle phi0 of the rainbow in terms of n. Hint: the derivative of arc sine x is 1 over square root from 1 minus x square. Solution. The condition for caustic is phi prime equals 0. From here we have this equation which gives us 4 multiplied by 1 minus x square equal n square minus x square. From here we have x equal square root from 4 minus n square over 3. And finally we can put this x to our expression for phi, and the result will be phi0 equal this expression. That was solution for question C. Question D. For water, the index of refraction of red light is 1.331 and the index of refraction for blue light is 1.340. Find the angular width of the rainbow on the screen and give your answer in degrees. Solution. Substantiating these two indices of refraction into the above equation and subtracting the results yield angle will be 1.30 degrees. That was solution for question D. Question E. A glory is an optical phenomenon which involves light scattered directly backward at p equal pi, leading to an apparent halo around the shadow of an observer's head. For what values of n is there a caustic for phi equal pi? Can glorious from water droplets be explained in terms of caustics? Solution. Referring to our answer above, we have a caustic whenever the denominator df over dx multiplied by sine phi, denominator d phi over dx multiplied by sine phi vanishes, and the sine phi vanishes for phi equal pi. Therefore, we will have a caustic at phi equal pi as long as light can be reflected backwards at all. It means whenever there is a solution for phi x equal 0, that is because at this angle all the outgoing light is directed at a single point on the screen. We thus need to solve arcsine x equal to arcsine x over n. Taking the sine of both sides and using the double angle formula gives this equation. Solving for n, giving n equal the square root. As the impact parameter x yielding the backward caustic range from 0 to 1, the values of n ranges from a maximum of 2 to a minimum of square root from 2. The index of refraction of water is outside this range, so glorious from water droplets cannot be explained in terms of caustics. The reason glorious are visible is still under debate. So that was solution for question E, and here we finish discussion for problem A3. US Physics Olympiad, year 2022, USAPHO, final round. Problem B1. Viral reality. The ideal gas law states that PVM equal RT, where Vm equal V over N is the volume per mole of gas. However, any real gas will exhibit deviations from the ideal gas law described by the viral expansion. This equation. For gases with low density, the higher order terms are negligible. So in this problem we will neglect all of the temperature dependent terms in parentheses except for Bt over Vm. The table below shows measurements of B for nitrogen gas N2 at atmospheric pressure P equal 1.01 multiplied by 10 power 5 pascals. Question A. According to the ideal gas law, what is the value of Vm at temperatures 100 Kelvin, 300 Kelvin and 600 Kelvin? Give your answers in SI units. Question B. What is the percentage change in Vm at these temperatures if one accounts for Bt? Question C. In 1910, van der Waals was awarded the Nobel Prize for formulating the equation like this, van der Waals equation, which accurately described many real gases. According to this equation, what is the form of Bt? You may assume that B much less than Vm. Question D. Using the data above, extract the values of A and B. Give your answers in SI units. Question E. In this problem, we have neglected terms in the viral expansion beyond Bt, which is a good approximation as long as the volume correction due to Bt itself is small. Assuming the van der Waals equation holds, numerically estimate the temperature's range within which the volume correction due to BT is at most 10% for nitrogen gas at atmospheric pressure. Solution for question A. According to the ideal gas law, what is the value of Vm at temperatures 100, 300 and 600 kelvins? Give you answer in SI units. Solution. Plugging in the values and converting to m³/mol to the ideal gas formula, we have Vm equal RT/P, or using SI units, we have next numbers for 100, 300 and 600 kelvins. That was solution for question A. Solution for question B. What is the percentage change in Vm at these temperatures of 1 accounts for BT? Solution. From ideal gas law we have Vm equal RT/P. From viral expansion for two first members we have this expression. The fractional change in volume is this one. Delta V over Vm approximately equal BT over Vm, which give us such percentage 100, 300 and 600 Kelvin. That was solution for question B. Solution for question C. In 1910, van der Waals was awarded the Nobel Prize for formulating the equation by his name, which accurately describes many real gases. According to this equation, what is the form of BT? You may assume that B much less than Vm. Solution. From van der Waals formula we have P plus A over Vm square equal RT over Vm minus B. For B much less than Vm we have approximately this formula, and rearranging it give us this approximation. Using this approximation we can conclude that BT equal B minus A over RT. That was solution for question C. Solution for question D. Using the data above, extract the values of A and B. Give you answers in SI units. Solution. First, we have to convert data points to SI units, which is giving us next table. Now, plotting B versus 1 over T, we will get this graph. The slope is negative A over R, and the y-intercept is B. So the final result is A equal 0.18 and B equal 6 by 10 power negative 5 in SI units. Any answer within 20% of this is acceptable. That was solution for question D. Solution for question E. In this problem we have neglected terms in the viral expansion beyond BT, which is a good approximation as long as the volume correction due to BT itself is small. Assuming the van der Waals equation holds, numerically estimate the temperature range within which the volume correction due to BT is at most 10% for nitrogen gas at atmospheric pressure. Solution. We are looking for the temperature range where BT approximately less than Vm over 10, which is approximately RT over 10P. At high temperatures, BT always yields a small correction for nitrogen at atmospheric pressure. At low temperatures, BT is dominated by member negative A over RT. So we require that T must be greater than square root from 10 Pascal over R, which is about 50 Kelvin. Any answer within 25% of this is acceptable. So that was solution for question E. US Physics Olympiad, year 2022, USAPHO. Final round. Problem B2. Broken vase. A uniformly charged ring of radius d has total charge Q and is fixed in place. A point charge negative Q of mass m is placed at its center. Both big Q and small q are positive. As a result, if the point charge is given a small velocity along the ring's axis of symmetry, it will oscillate about the ring's center. Question A. Find the period t of the oscillations. For the rest of the problem, we will consider this situation in a reference frame where the ring is moving along its axis of symmetry with a constant speed v, which may be comparable to the speed of light c. In this frame, the ring and the point charge have a charge big Q prime and small q prime, and the point charge still oscillates about the ring's center. Question B. What is the period t prime of oscillation of the point charge in this frame? Question C. When the charge is a small distance dx from the center of the ring, find the restoring force in terms of small q prime, big Q prime, v, d, and dx, and the fundamental constants. Question D. Suppose the restoring force has the form F equal negative k dx. Find the period of the resulting oscillations in terms of k, m, v, and the fundamental constants. Question E. Suppose the electric charge transforms between reference frames as q prime equal gamma power n q and small q prime equal gamma power n small q. By combining your answers to parts C and D and comparing to part B, find the value of n. To solve this problem, you will need the following results from relativity. The Lorentz factor is defined as gamma equal 1 over square root from 1 minus v square over c square. The momentum of a particle is p equal gamma mv, and m is the same in all frames. The electromagnetic force on the charge q is F equal dp over dt equal q multiplied by E plus a cross product V and B. The electric field of a charge q at the origin with a constant velocity V is radial with the magnitude E equal this expression, where theta is the angle of R to V. Solution for question A. Find the period t of the oscillations. Solution. Suppose the charge is displaced by a small distance delta x in a horizontal direction. Electric field from total charge q on distance d multiplied by sine small angle theta, which is approximately delta x over d. That will be this expression, proportional to dx. In that case, restoring force will be this one. And direction is opposite to displacement, because the charge is negative. And now we can rewrite it in form of acceleration proportional to displacement and the opposite direction. This is a completely formula for harmonic oscillation, where omega square equal this coefficient, where omega is angular frequency. So from here we can find what is the period. Period will be 2 pi over omega, or this square root. That was solution for question A. Solution for question B. What is the period T prime of oscillation of the point charge in this frame? Solution. By directly applying time dilation to the answer of part A, we have T prime equal gamma T, or 1 over square root from 1 minus V square over C square multiplied by answer in the previous question. That was solution for question B. Solution for question C. When the charge is a small distance delta x from the center of the ring, find the restoring force in terms of small q prime, big Q prime, V, D, delta x, and the fundamental constants. Solution. The position of the charge relative to each charge in the ring is almost 90 degrees. Thus, using the provided information, we have electric field from the ring in x direction equal this expression, where pi over 2 minus theta is very close to 90 degrees. So we can neglect this one and equalize sign to 1. In that case we have this expression, which can be simplified to this one. Thus the restoring force is this one. So that was a solution for question C. Solution for question D. Suppose the restoring force has the form F equal negative K delta x. Find the period of the resulting oscillations in terms of K, M, V, and fundamental constants. Solution. By the definition of force given in the information below, we have force equal delta P over delta T, or M multiplied by derivative from V over square root from 1 minus V square over C square. Carrying out the derivative and the simplifying give us F equal this expression. For small oscillations, the velocity is always approximately equal to the original velocity V. Thus, the motion is still simple harmonic, because acceleration is still almost proportional to displacement, with the coefficient equal omega square. It means that period equal this expression. So that was a solution for question D. Solution for question E. Suppose the electric charge transforms between reference frames as Q big prime equal gamma power n Q big and Q small prime equal gamma power n Q small. By combining your answers to parts C and D and comparing to part B, find the value of n. Solution. From final result part C, we have restoring force proportional to displacement. It means that coefficient of proportionality equal this expression. From part D, we found that if we know what is coefficient of proportionality, we have period equal this expression. Now, plugging this K to our last formula, we have period equal this expression. But this is the same result as in part B, this one. If we have that Q big prime multiplied by Q small prime equal Q big multiplied by Q small. And this is true when power n equal 0. So it means that electric charge is a Lorentz invariant. That was solution for question E, and here we finished discussion for problem B2. US Physics Olympiad, year 2022, USAPHO, final round. Problem B3. Time crystal. The kinetic energy E, momentum P, and velocity V of a particle moving in one dimension satisfy F equal delta P over delta T, which is equal to delta E over delta X, and V equal delta E over delta P, where F is the external force. For a free particle, the momentum and energy are related by E equal P square over 2m. However, when an electron moves inside a metal, its interactions with the crystal lattice of positively charged ions lead to a different relationship between momentum and energy. All of the above identifiers still apply, but now suppose that energy as a function of P equal V multiplied by 1 minus cosine Pb, where V and B are constants that depend on the metal. This result is inherently quantum mechanical in origin, and as we will see, it leads to some rather strange behavior. Question A. First we investigate the motion of the electron in general. First, find the velocity as a function of P. Second, the effective mass m of the electron is defined so that it satisfies F equal m star A. Find the effective mass as a function of P. Question B. Now suppose a metal rod of infinite length aligned with the x-axis contains conducting electrons of charge negative E, initially with a zero momentum. At time t equals 0, an electric field E equal E0 multiplied by unit vector x is turned on and is experienced by every electron in the rod. Ignore the interaction of the electrons with each other. First, for an electron that starts at x equals 0, at time equals 0, find its position x as a function of time. Second, if the number of conducting electrons per unit volume is n and the cross-sectional area of the rod is A, find the average current in the rod over a long time. Third, now suppose that every time tau, each electron suffers a collision with the crystal lattice, causing its momentum to reset to 0. In the limit of frequent collisions, charge of electron E multiplied by E0 B tau much less than 1. Find the average current in the rod over a long time. Fourth, if tau can be freely adjusted, estimate the maximum possible average current in the rod up to a dimensionless constant. Solution for question A. First, we investigate the motion of the electron in general. First, find the velocity as a function of P. Solution. Using the provided identity, we have V equal delta E over delta P, and using expression for energy, we have this formula. We need to take first derivative, which will get us formula that V equal big V B sine EB. That was a solution for the first one. Second one, the effective mass m star of the electron is defined so that it satisfies equation F equal m star A. Find the effective mass as a function of p. Solution. By definition, we have force F equal delta p over delta t, which is m star multiplied by acceleration, which is delta v over delta t. So by the chain rule, we have delta p over delta t equal delta p over delta v multiplied by acceleration delta v over delta t, and putting this expression to the first formula and cancelling delta v over delta t, we have m star equal delta p over delta v. But we already know what is the v as a function of p, so we can take reverse function and write this expression, which give us finally this one. So finally m star equal 1 over vb square multiplied by cosine pb. Note that at some points this mass is negative. Applying a forward force can cause an electron to accelerate backwards, which leads to the strange result we will find in part B2. This doesn't contradict conservation of momentum, because the forward momentum ends up imparted to the crystal lattice, causing the solid as a whole to recoil. So that was a solution for second question. So we finished discussion for question A. Solution for question B. Now suppose a metal rod of infinite length aligned with the x-axis contains conducting electrons of charge negative e, initially with a zero momentum. At time t equal 0, and electric field E equal E0 multiplied by unit vector x is turned on and is experienced by every electron in the rod. Ignore the interactions of the electrons with each other. First, for an electron that starts at x equals 0 at time t equals 0, find its position x as a function of time t. Solution. The momentum is force F multiplied by time t, which is negative E multiplied by E0 t. So using the result of part A1, we have V as a function of t equal this expression. Integrating both parts, we have x as a function of t equal this expression, which is solution for the first question. Question 2. If the number of conducting electrons per unit volume is n and the cross-sectional area of the rod is A, find the average current in the rod over a long time. Solution. If we look at this function as a function of t, we can find that electrons just oscillate, not moving further than some kind of fixed region. So it means that the average velocity is 0, therefore the average current they supply is 0. This strange phenomenon is called Bloch oscillation. It doesn't occur in original metals because of the frequent collisions between electrons and ions considered in the parts below. That was solution for the second question in part B. Third, now suppose that every time tau, each electron suffers a collision with the crystal lattice, causing its momentum to reset to 0. In the limit of frequent collisions, E multiplied by E0 b tau much less than 1. Find the average current in the rod over a long time. Solution. For small times, the velocity is approximately this one, where we applied the small angle approximation to the result of part Bi. Thus, if collisions happen every time tau, average velocity is this one. Therefore, the average current, this expression. The plus sign makes sense since it means the current flows parallel to the applied field. That was solution for the third one. Number 4. If tau can be freely adjusted, estimate the maximum possible average current in the rod up to a dimensionless constant. Solution. If tau is small, then more frequent collisions slow down the current as we show it in part B3. But if tau is very large, then the current cancels itself out due to Bloch oscillations. As we show it in part B2, therefore the highest possible current occurs when the electrons have time to accelerate to a substantial fraction of the maximum possible speed Vb, but collide before their effective mass goes negative. This occurs when E multiplied by E0 tau b is order of 1, and that gives an average current order of Na EVB. Some students try to answer this part using dimensional analysis, but that won't work since there are 5 variables and only 4 independent dimensions: mass, length, time, and charge. Incidentally, you can find the dimensionless coefficient by solving a simple equation numerically, though this wasn't required. That was a solution for all part B, and now we finished discussion for problem B3.